afternoon. I'm Gunter Mark. I'm a research master student at Von Karman Institute. And today I will speak about the my communication analysis on CubeSat space mission. This presentation I will give you a short introduction on CubeSat, and I will show you the main results of my research through the study of the possible communication solutions, the study of the orbital inclination and ground station latitude influence, and I will explain some problems like the communication overlaps presence, and I will conclude with the constellation problem, which describes the real mission behavior. Okay, CubeSat mission is a very interesting space mission. It has the main objective to study the lower thermosphere by a network of 50 CubeSats. These satellites will be launched together in a circular orbit at the altitude of 380 kilometers, and they will collect data from the atmosphere, and they will communicate with a ground segment network. The communication is a real challenge for this mission because we need a totally new kind of communication analysis, because we have to manage 50 CubeSats with decaying orbits, and especially the achievement of mission requirements is far to be easy with the low technologies that are involved. The main objective of my work were the evaluation of the number and positions of ground stations required to satisfy mission requirements, and this optimization of the communication link between the ground segment and the space segment. The main requirements are the use of a simple and high space qualified technology, and especially the 2 megabits of science data per day done to the Earth for each CubeSat, 4 megabits if we include the team payload, and 10 megabits if we include also other margins. Okay, the methodology is divided mainly in 3 points. First one is the one-to-one problem, in which I analyze the communication behavior between one CubeSat and one ground station. The second step is the study of the communication overlaps, which can occur when we have close CubeSats. And in the end, there is the constellation problem, which includes all the previous points. Okay, the first point of the one-to-one problem is the communication system selection. I mainly compare 2 different systems, the UHF-VHF system and the S-band system. And for both strategies, I analyzed 2 different configurations of ground station, a fixed ground station and a ground station with a rotator mechanism, in order to follow the satellite during its transit. By STK software, I calculated the access time and the accumulated data, and I did also a final comparison on the signal quality by the link budget analysis. So in the end of this process, I was able to select my system architecture. And here we can see the advantages and the disadvantages of the 2 systems. UHF-VHF system has good points like the low power consumption, and it is very high space qualified for CubeSat application. But it has also a very low data rate with respect to other systems like the S-band that has a very good data rate, but it has also a very high power consumption and a narrow beamwidth. So I mainly performed 2 simulations on STK, one for a fixed ground station and one for a ground station with a rotator mechanism. Okay, from these simulations I saw that the results for a fixed ground station are far to be feasible, and the result, and it suggested me to implement the rotator on the ground station for our architecture. In the link budget analysis, the system link margin played a primary role, because if this parameter is low, we need to increase the complexity on board of the satellite. So it is recommended to have a system link margin for low-cost system, which is higher than 10 decibels. For the UHF-VHF system, we don't have problem, but for the S-band system, we found problems. So the outputs suggested me to use a UHF-VHF system with the related ground segment and space segment devices. Always in the one-to-one problem, I evaluated the importance of the orbit inclination, because if we change launcher, or if there are some mission modification, it is useful to have a general review of the possible communication performances. So using SDK software, I evaluated the communication behavior for different inclinations between 60 degrees and 100 degrees, assuming to have only one ground station at VKI. Okay, as we can see, lower inclination ensure more transmitted data, and they can reach also more than the 70% of data transmitted for low inclination with respect to the higher. Another important investigation was on the ground station position. If we change the position of our ground station, the accumulated data change deeply. So here it's extremely useful to have an overview of possible performances. So I assume to have 9 ideal ground stations on the same meridian to understand the effect of the ground station latitude. And as we can see for our mission, the higher latitudes ensure more transmitted data. Because as we can see from the right picture, the picture on the right, higher latitude ground station can offer a larger coverage area. And we can also transmit more data of 7 times or 8 times more for higher latitudes. So if we extend the number of the satellite and we increase it, the first problem that we find is the overlap problem, because we have the big constraint that only one ground station can communicate with one CubeSat per time. So if we have 3 CubeSat in view of a single ground station, we will lose data. So I performed a simulation on SDK with 2 CubeSat with a difference in this angular distance between each other, and assuming only one ground station at VKI, I found that obviously if we have higher angular distances, overlaps are shorter, and close CubeSat so will require more ground station in order to avoid this problem of the overlaps. So interpolating these results, I was able to find the minimum angle between CubeSat to avoid this problem of the overlap. Assuming to have an average contact time of 200 seconds, I found a region in which we have for sure overlaps, an ideal one in which I didn't take into account the time to rotate the antenna to the starting position. But if we add this time, we can find the real overlaps absence region that is characterized by a minimum angle difference of 18 degrees. But especially from this analysis, I was able to have a direct analytical knowledge of this problem, that it was very useful to extend this problem to the constellation problem. The main problem for the constellation is that the constellation geometry varies with time. So I introduced 2 different groups of CubeSat. The first one, group 1, for larger angular distance between CubeSat, and the second one with closer distances between CubeSat. So post-processing SDK results by MATLAB, I performed a lot of analysis on the constellation problem, but for sure the most important was the combination analysis, in which I analyzed the communication behavior for some possible combinations of ground segments with an increasing number of ground stations between one station, a single station, to 25 ground stations, including the suitable ground station of QB50 partners. Okay, here we have the result for a single ground station, highlighted with the line, the green line, the minimum data per day accumulated during the whole mission, and with the red one, the communication threshold of 10 megabits per day. So we are far to reach the mission requirements. As we can see also from this plot, there are a lot of low peaks under the 10 megabit line. So we have to increase the number of stations to increase the accumulated data. For example, if we select 10 ground stations, we have that the results are very good, but we have to take into account that if we are too much low, about the 10 megabit line, we are wasting resources. So I interpolated the results, and I found that 3 ground stations is the optimal number of ground stations to satisfy mission requirements. So with 3 ground stations we are able to reach mission requirements, and we will not have a waste of resources, so the mission costs are quite low. Looking also the good results for the high latitude ground station, it was interesting also understand the communication behavior for only 1 ground station, but at very high latitudes. So I introduced 3 new ideal ground stations close to the North Pole with same orbital characteristics and mission requirements, and the results were feasible. But for the second group, in which we have the closer CubeSat, we have also a strong effect of the communication overlaps. So first satellites will communicate better than the last. So concluding by this analysis, it was possible to select the system for our communication architecture, the UHF-VHF system. It was possible to study deeply the influence of the overlaps and ground station position and orbital inclination. And it was also interesting to investigate the behavior of a single ground station at very high latitudes, but it has some downsides, like the strong overlaps effect, and it's also difficult to reach, so we have difficulties in the accessibility and in the maintenance, which increase the cost of the mission. So cost of the mission that stayed down for the use of the 3 ground station of QB50 partners. So just to conclude, I would like to thank VKI QB50 team and ISA for the sponsorship. Thank you.
Thank you. Are there any questions? No questions? Okay, thank you very much again.